This is one of the most powerful jet engines on Earth. And believe it or not, it runs at temperatures 250 degrees Celsius hotter than the melting point of the very metals inside it. We're talking about 1,500 degrees Celsius. So the big question is, why doesn't it just melt into a puddle of goo? Every single time you board a plane, this incredible feat of engineering is happening right beneath your feet. As we speak, there are probably more than 10,000 planes in the sky, all powered by engines just like this one. It's a technology we rely on daily, but how many of us actually know how it works? Let's break it down. This is a turbofan jet engine. Right at the front, you'll see a massive fan. During takeoff, this fan is a beast, pushing about 1.3 tons of air backwards every single second. But here is something you might not know. Only about 10% of that air actually goes inside the engine core. The other 90% bypasses it, which we'll get back to later. The air that does enter the core gets funneled into the compressors. These are a series of spinning blades that squeeze the air, compressing it to about 50 times normal atmospheric pressure. This compression process naturally heats the air up to around 600 degrees Celsius. From there, this super hot, high-pressure air is blasted into the combustion chamber. Fuel is sprayed in and ignited, and the temperature spikes to a blistering 1,500 degrees. This creates a high-energy gas that wants to explode outwards in every direction. But there's only one way for it to go, out the back. Before it can escape, though, it has to push its way past rows and rows of turbine blades, and this is where the real magic of a jet engine happens. During takeoff, a single one of these turbine blades produces the same amount of power as a Formula One car, a single blade. And there are dozens of them inside the engine. As the scorching hot gas expands, its pressure drops from 50 atmospheres all the way down to 1, expanding to 20 times its original volume. This process spins the turbine at an incredible 12,500 revolutions per minute. This spinning turbine is what powers everything at the front of the engine, the giant fan and all the compressor stages. It's a self-sustaining loop, and as the remaining exhaust gas shoots out the back, we get thrust, pushing the plane forward. Except, here's the twist. You might think all that fiery exhaust is what provides most of the power. But actually, about 80% of a modern jet engine's thrust comes from that big fan at the front, the one that bypasses the core. Only 20% is true jet thrust from the hot exhaust. Why is that? Well, it turns out it's far more efficient to push a large mass of air backward slowly than it is to push a small mass of air backward very fast. It's simple physics, and it's the reason modern jet engines have gotten bigger and bigger over the years. They are all about moving huge amounts of air. The efficiency of any heat engine is fundamentally limited by something called Carnot efficiency. In simple terms, it's about the difference between the cold temperature of the outside air and the hot temperature of the gas inside the engine. The bigger that difference, the more efficient the engine becomes. So, the goal is always to run the engine as hot as physically possible. But running hotter creates one of the most extreme environments humans have ever engineered a machine to survive. A single turbine blade has to withstand gas at 1,500 degrees Celsius, all while spinning at 12,500 RPM. The tips of these blades are moving at nearly 1,900 kilometers per hour. The centrifugal forces are immense, equivalent to 20 metric tons, the weight of a double-decker bus pulling on each blade. On top of all that, it's constantly being blasted by sand, dust, and corrosive oxygen. And yet, these blades are expected to last for tens of thousands of flight hours without failing. So how is this even possible? Why don't they just fail? Your first thought might be to use really tough metals. What about steel? Nope, steel starts to fail and deform around 600 to 700 degrees. What about titanium? It's lighter, but it fails at even lower temperatures. You could try tungsten, which has an incredibly high melting point of over 3,400 degrees. But it's far too heavy and brittle to spin at those speeds. Clearly, conventional metals weren't going to cut it. Engineers needed to invent something entirely new. And that's what they did. Enter the era of nickel-based superalloys. Scientists discovered that by taking nickel and adding specific elements like chromium, Cobalt, and especially aluminum, they could create a remarkable microscopic structure. It consists of two distinct phases, a soft, pliable matrix called gamma, which acts like a road system, and incredibly strong, ordered blocks called gamma prime, which are embedded within it. In any metal, there are tiny atomic defects called dislocations. When the metal is under stress, these dislocations move, which is what causes it to bend and break. But in a superalloy, these dislocations get trapped by the hard gamma prime blocks. They can't move. And here's the amazing part. This effect makes the alloy stronger as it gets hotter, reaching its peak strength around 800 to 1000 degrees Celsius. Other elements are added to fine-tune its properties. Chromium provides resistance to oxidation. Cobalt and titanium help stabilize the strong gamma prime structure. Molybdenum strengthens the surrounding matrix. And then there's rhenium, a super rare and expensive element. It provides extreme resistance to a slow deformation process called creep. In fact, 80% of all the rhenium mined in the world goes directly into making jet engine components. But even with these incredible superalloys, one fundamental problem remained. The enemy was something called grain boundaries. All normal metals are polycrystalline, meaning they're made of millions of tiny individual crystal grains packed together. The borders where these grains meet are called grain boundaries, and they are the material's weakest points. This is where cracks start, where atoms diffuse away, and where creep accelerates under high temperatures and stress. A turbine blade made of a normal grainy metal was still doomed to fail. So, engineers at Rolls-Royce and other companies asked a radical question: what if we could make the entire blade out of one single, perfect crystal? And they figured out a way to do it. The process is mind-blowing. It starts with a precise wax model of the turbine blade. This wax model is then dipped repeatedly into a ceramic slurry, building up layers to create a strong ceramic mold. Once the mold is complete, the wax is melted out, leaving behind a perfectly shaped hollow cavity. Then, the molten superalloy is poured in at the exact same searing temperature found inside a real jet engine. At the very bottom of the mold is a water-cooled copper plate. As the molten metal touches this chill plate, crystals begin to form and grow upwards. The entire mold is then slowly, very slowly, lowered out of the furnace, allowing the metal to solidify from the bottom to the top. But this would still create multiple crystal grains. The real genius was in eliminating all of them except one. To do this, engineers invented something that looks like a little spiral or a pigtail at the base of the mold. As the crystals grow upwards through this spiral, they are forced to compete with each other. The geometry of the spiral is designed so that only one single crystal can win this race and make it into the main blade cavity. What emerges is a finished turbine blade made of one single crystal. That's 6 times 10 to the power of 24 atoms, all perfectly aligned in a single, flawless lattice. After a final heat treatment process, the gamma and gamma prime phases form their ideal strengthening microstructure. The result is staggering. A single crystal blade has 9 times better resistance to creep and 3 times better corrosion resistance than its polycrystalline predecessor. It can survive for over 25,000 flight hours. Without single crystal blade technology, modern jet engines would simply be impossible. The impact has been huge. Between 1960 and 2010, jet engines became 55% more fuel efficient. The primary reason for this leap was the ability to run turbines hotter and hotter, a feat made possible by the development of single crystal superalloys. So, the next time you're flying gazing out the window at 35,000 feet, you can appreciate that your journey is safe, comfortable, and reliable because of a tiny, perfectly engineered piece of metal that refuses to melt even while living right on the very edge of what is physically possible. Thanks so much for watching. If you enjoyed learning about this incredible technology, be sure to like and subscribe MindFacts for more deep dives into the world of engineering.